Okay, this is the lecture video for MAC 1105, section 4.2 in My Open Math. In this section, we're going to be taking a look at polynomial functions and their graphs. First, let's take a look at the definition of a polynomial function so we can see what's considered a polynomial function. The main thing is that all of the powers on the functions have to be non-negative integers. Okay, every single exponent on a variable has to be an integer, can't be a fraction, can't be a decimal, and it has to be positive. That's the main thing that you're going to be looking at as you go to tell what's a polynomial function versus what is not a polynomial function. You're going to be expected to understand what the degree of the function is. So I've written for you here that the degree of a function is just whatever the highest degree is. So you're going to look through all the terms, locate the term that has the highest power on the variable, and that's the degree of the overall function. Because based on this degree, as well as the leading coefficient, and let me go over that, whatever the highest degree variable is, the number in front of it is called the leading coefficient. Because using these two items, the degree of the function as well as the leading coefficient, is going to tell you what the ends of the graph are doing, because you're going to be graphing these things by hand. So you're going to be expected to understand end behavior. Okay, here's some examples of functions that are considered polynomial versus functions that are not considered polynomial. Notice that every single power on a variable, notice that they're positive and they're integers. The leading coefficient in this case would be -3. The degree is whatever the highest power is, highest power on the variable. So this is a polynomial function of degree 5, and the leading coefficient is -3. Down below, you see a function that started off as a product, and by the time it was all multiplied out, this was the overall function. Highest degree here is 6, therefore this is called a polynomial function of degree 6, and the leading coefficient is -3, as opposed to these functions which do not serve as polynomial functions. The reason that this is not a polynomial function is because the square root of x is the same thing as x to the 1/2. So this is not considered a polynomial function. No need to tell anyone what the degree is or the leading coefficient, because they're only going to ask those questions when it's a polynomial function. Okay, this is also an example of something that's not a polynomial function, because the first term is -3 over x squared, and if you recall, any variable to a power, any kind of power, whether it's attached to a variable or not, is really a negative power when it's in the denominator. When you have x squared in your denominator, that is the same thing when you take it out of fraction form as x raised to a power of -2. And those exponents may not be negative. They have to be non-negative. So because of this right here, this is not a polynomial function. And because of the power here being a fraction instead of an integer, this is not a polynomial function. Reviewing some of the functions that we have worked with up until this point, they have been the topic of the previous chapters that we've covered, and those were lines. We talked about the horizontal line. This is a function that describes a horizontal line, y equal to 3. If you plotted a bunch of points where all the y coordinates with 3 were 3, they would line up in a horizontal fashion. So we've studied that function. We've also studied this function where you have both a y and an x in your equation. This can be written as y, this can be written as 2x. When you have a y and an x in your equation, you then have a slanted line, as opposed to this function, which only has one variable in it, just the y. I won't talk about just x, because that is not a function. When you have just x equal to a number, that's a vertical line and is not considered a function, and we're talking about functions here. So this would give you the slanted line, and then this was the topic of the section right before this. Y is equal to negative x squared plus 1. Anytime you have any kind of a squared term, you're talking about a parabolic shape. And we did a lot of examples in section 4.1 concerning parabolic graphing by hand. In this section, we're going to go beyond all of this. We're going to go to graphing third degree and higher. You're going to be expected to understand what the ends are doing. That's called end behavior. You're also going to be expected to be able to find where it hits the x-axis, where it hits the y-axis, and you're also going to be expected to understand things like the multiplicity of the zeros. Zeros is just another name for X intercepts, and you're going to be expected to know what is happening at each of those X intercepts. Does the graph touch the X intercept and bounce right off of it, or does the graph go right through it? In other words, right through the x-axis. So we're going to be making distinctions like that, and again, you'll be producing the graph by hand. So first thing on your way to producing these graphs by hand is to understand what they look like in general. Polynomial graphs are nice, smooth functions rounded at each of their turning points rather than having sharp turns like this. There are no breaks in the graph. It's a smooth, continuous graph, whereas this is called a piecewise graph. This is something that was on a previous test that you took, where you would graph the function in pieces and there's a break in the graph. Polynomial functions never look like that. Polynomial functions, regarding their ends, either end of the function, they will either go in opposing directions, like this example that you see here. Right side goes up, left side goes down, or they'll both go in the same direction. In this particular example, both ends go up, the left and the right side of the graph. So you're going to learn how to figure out all of that as you create your own graphs. We're going to use, in order to figure out what the ends are doing, the leading coefficient test. Okay, so here are the things that you are looking for to determine what the ends are doing, what the left end and the right end are doing on your graph. First, let's look at anything that is of an odd degree. That's what they mean by n is odd, because n refers to what is the highest degree, the term with the highest power. So whenever that highest power is odd, that means the degree of the function is odd. So if the leading coefficient is positive, that'll just be the coefficient in front of the variable with the highest degree. So let's say the highest degree is odd, like x to the third degree, and the leading coefficient is positive. That's what it means for something to be greater than 0. Try to make this a little bit bigger so you can look at it. So when you're in this situation right here, where the leading coefficient is positive and you're of odd degree, that means the right side goes up and the left side goes down. You're going to need to memorize these end behavior cases. If your highest degree is odd, highest power is an odd number, but yet the coefficient in front of it is negative, this means leading coefficient is negative. If that's the case, then what would happen, instead of right side going up and left side going down, it would be the reverse of that. Left would go up, the right would go down. So maybe you can memorize this one and just reverse it to know the other case. This is when your leading coefficient is a positive number. The number out in front of the highest degree is a positive number. And this would be the reverse of it. Notice that what these two have in common is that they both have end behavior that opposes each other. Up on the right, down on the left. See how they go in opposite directions? That is always the case when the highest degree is odd. On the other hand, let's say that the highest degree is even. Okay, degree of the overall function, being that it comes from whatever the highest degree is, if it is even, and your leading coefficient is positive, that means that both of the ends will go up. However, if the degree is even and your leading coefficient is negative, that means that both of the ends go down. Notice the relationship of these two. Anytime your degree is even, that means both of the ends move in the same direction. These both go up, and that's because the leading coefficient is positive. These both go down, and that's because the leading coefficient is negative. Okay, so just a little bit about end behavior. Every time I do one of these problems, I'm going to remind you that you are in one of these four cases and remind you about what the ends are doing, because you're going to need to know that so that you can properly complete the graph in each of these problems. Okay, let's go to this first example. This is the function that you're being given right here. This is the degree. It's whatever the degree is on whatever the highest degree is, and the leading coefficient is 1. So what is the degree of the polynomial? It is odd, and that's because it's third degree. What is the leading coefficient in this particular problem? 1. It's whatever the coefficient is of the term with the highest degree. Determine the end behavior. Well, whenever the degree is odd, the way it is right now, and the leading coefficient, see, it's a combination of these two things that you're looking at. Degree is odd. Leading coefficient is positive. That means that the right side goes up and the left side goes down. Does the right side of the graph rise or fall? Well, when something's going up, that means it's rising. So you're going to figure out what's going on in the middle, but this is basically what it looks like whenever you have odd degree, leading coefficient is positive. Up on the right, down on the left. So what is the right side doing? This is the right side. This is the left, considered the left side. If you were put your pencil right here, you'd have a right and a left. Okay, so the left side is falling. This is rising, and the left side is considered falling. Use your calculator to confirm your answer. You may have to manually adjust the window to see the entire graph. So this will teach you to be able to adjust your window manually. When you're trying to see the ends of a graph, let's go ahead and try this. Let's quit out of here and go to y is equal to. So I'm going to put in x raised up to a power of 3 plus 3x squared minus x minus 3. Press enter after you get done. You can start with Zoom standard. Under the Zoom key, it's pre-made windows, and then you can adjust manually from there. See, like this is perfectly fine because you can, just by using Zoom standard, you can already see what we already knew. So it is in your best interest to memorize. Well, you have to memorize or you won't be able to do any of the graphs by hand. What the ends are doing. This goes up on the right and down on the left, and that's exactly what we said here. So we've confirmed with our calculator the end behavior. Okay, this is the next example. Use leading coefficient, again, and end behavior to determine the end behavior of the graph. Okay, so is the degree of the polynomial odd or even? So I've given you this example so you know what to do when you see that you have different factors that make up the polynomial function. In this case, if you want to know what the degree is, you need to add up these powers on the x. Here you have an x to the third degree. Here you have, if you were to FOIL this out, no need to actually do that, But if you were to FOIL this out, you would have one term that was x to the second degree, which would eventually get multiplied by this, and then you'd have another x to the first degree, which would be multiplied by those. So add up these powers, and that means the term with the highest degree, if you were to FOIL all of this out, would be x to the sixth degree. So this would be your highest degree, and therefore this is a polynomial of even degree. Okay, so even. It was highest term would be 6th degree on that x if you were to FOIL all of that out. What is the leading coefficient? Well, let's see here. Again, as far as what is the variable and what is its degree, the variable is x here. You can see that. And eventually, as you FOIL this out, you would be going at some point x to the third degree times x squared times x to the first degree. So on your variable, that would be the highest degree, as I've already explained. And the leading coefficient on that term with the highest degree would be -4 times 1 times 1. So this would be your leading coefficient right here. Okay, -4 times 1 times 1. That would all of that would happen in the process of FOILing this all out, but like I said, there's no need to actually go through that because that would be a lot of work. But you do have to know how to get the highest degree on your variable. You just add the exponents and what the leading coefficient would be. So this would be -4. Determine the end behavior. Again, it is you're considering both of these things at the same time. Because it's even degree, both ends move in the same direction, as opposed to moving in different directions, like when it's odd degree. Both ends go in the same direction. Now, because they're negative, they both go down like this, and then you'd be figuring out as you go through all the details of graphing what is happening in between that. But as far as the ends go, they both go down. So determine the end behavior. Does the right end of the graph rise or fall? When something goes down, that's considered falling. So not only does the right side fall, but so does the left, because they're both ends are moving in the same direction. So this falls, this falls. The right side as well as the left side. Use your calculator to confirm your answer. Okay, so let's plug it in just like this. We're going to get a look at this graph. So it's -4x cubed times x minus 1. Close it up, put a square on it, times x plus 5. Close that up. Enter, and you can start with Zoom Standard if you like and just adjust from there. Okay, like, what I'm seeing here is, I think I'm seeing both ends, but you have too much over here and too much over here. You'll be able to see the graph a little bit more clearly if you don't have so many numbers on your x-axis. This goes from -10 to 10. I'm going to put less numbers on here. Like this one goes out to -1, 2, 3, 4, 5. I'm going to go out from -6 to 2 because that's like a 1 right there. So manually adjusting the window. I want my x-axis to go from -6 to 2, just so it's a little bit more spread out and I can see it a little bit better. All right, so it's a little bit better. So I'm not seeing the top, but I don't need to see the top right now. And you can see that this end goes down, and you can more clearly see that that end goes down. And that's exactly what we had already predicted anyway from our knowledge of the leading coefficient theorem. Okay, so we've confirmed that with our graph. Next example. This was the graph of f of x, -x to the 4th degree. So this is an even degree. That's the highest degree here. And the leading coefficient is negative. Okay, so anytime it's even degree, the ends move in the same direction, either both up or both down. because this is negative, they're both going to go down. So you should be able to predict it before you even touch your calculator. So this is saying the graph of this was obtained using a graphing utility and a window of -8 by 8 by 1. This is for the x's. The first window they mention is always for the x's, and this is for the y's. Let me remind you from one of the sections in the very first chapter that we did, this is x min. The second number stands for x max, and this is what we call the x scale. Likewise, this is y min, y max, y scale. It's always the order in which they give the number. Is this complete graph? Is this a complete graph that shows the end behavior of the graph? Well, we already know that if you understand the leading coefficient theorem, that both ends should go down. So would this give a graph that would allow us to actually see what the ends are doing? That's what this question's asking. So let's see. We can put this into the graphing calculator by going to y is equal to, clearing out what's there and feeding in this function, negative x raised to a power of 4, then it's plus 8x cubed plus 4x squared plus 2. And then we can graph it, and let's put the window that they were talking about. Let's go to window and put in, from our x's, -8, x min, or no, that was the x min, -8, x max is this +8, and then the x scale is 1. Then for our y values, our y min is -10, +10, and y scale is +1. Those numbers are already there. So we can second quit to go out of this screen and regraph using the window that they were saying. So they're saying that this was put in the graphing calculator. This is the graph that it produced. And the question is this a complete graph that shows the end behavior of the graph? No. We already know that both ends should go down. But because there isn't enough of a y-axis, you never get to see it come down again. We can see this end coming down. This is going in a downward direction. But because there's not enough over here, you would need a much bigger positive x-axis in order to give this room to come down again. So if you did want to see what that looked like, you could always go zoom fit. You could go zoom and make that graph fit in the window. Oops, went too far. You can get a kind of an idea of, yeah, it does have two ends, and you still can't see it. This doesn't even go far enough. I'm going to let this thing go all the way out to 10, 11, 12. I'm going to take it out to 12. So I'm going to do a window of X max. Let's see where it's at right now. It only goes to 8. Let me give it some more room on that side so we can truly see that both ends come down. Okay, you don't need any of the upper y-axis because that's not what we're being asked about. But now you can see that both ends come down. So be careful. Try to grasp onto how to manipulate your calculator by messing around with the window manually so that you are seeing the graph. And the only way to know if you're seeing the graph so that you can answer the questions properly is to know what the ends are doing. If you see that you have a graph and your ends are not doing what you predicted they should be doing, then you need to manually control the window so that you can see both of the ends. So this, we said, does this show the end behavior of the graph? No. Explain your answer. Both ends should fall. Yet this particular window that was chosen, a negative 8 by 8 by 1 by negative 10, 10, 1, does not allow you to see the ends. It shows you the left end, but it doesn't show the right end. Okay, moving on to the next example. I'm just talking a little bit about being able to tell what the ends are doing. Okay, here's another example. Goes a little bit further, getting you ready to produce your own graphs. For the given function, create a graph by hand, discuss the end behavior of the graph, show all algebraic calculations for the x-intercepts and the y-intercepts. And whatever you see me doing here, as always, is what you should be able to do on a test. That's what these lectures are for, to help you get through the homework, but also to help you perform, more importantly, on the test, since they count for much more than just doing the homework. Because the homework, let's face it, it's open book. You can look at videos, you can look at anything. The test is the true determination of whether you know what you're doing. So make sure you're not relying on your calculator for every little thing you do, and that you can demonstrate what's being shown in these videos. Okay, is the degree of the polynomial odd or even? Well, this is the highest degree, it's odd, therefore this polynomial is considered odd. I'm just going to circle it. What is the leading coefficient? The coefficient in front of it, 1. Determine the end behavior. Anytime that it is odd degree and the leading coefficient happens to be a number that is positive, anything greater than 0 is considered positive. That's why I'm writing it like that. So this is the leading coefficient. It was equal to 1. That's a number that's positive. So that means that the right side goes up. So it rises. You can just circle it if you want. And the left side of the graph falls. And then, it connects in the middle. And you get the details on that as you, begin to do all the other things like the Y-intercept and the X intercept. You get more specific details. But as far as what's going on the right side of the graph, it rises. What is it doing on the left side? It falls. Find the X intercepts, also called the zeros, by allowing the function to be equal to 0. You always let y be equal to 0 whenever you're finding the x-intercepts. So doing that now for this example, f of x stands for the y. I'm going to let that be 0, and I'm going to copy the right side. Okay, so if I wanted to find the zeros, that's just also another name for the solutions. And when you are finding solutions of second degree or higher, the most common technique, almost everything we do, is to factor. Whenever you have 4 terms like this, it is factor by grouping. So I'm going to take x squared out of the first 2 terms, take it out, put 1 parenthesis next to it, use what you've taken out, the greatest common factor, as a multiplier to get back each of those terms. So x squared times x would get that back. X squared times 3 would get the 3x squared back. Come to the back 2 terms and do the same thing. Take out the greatest common factor, which is -1. Both of these terms have a -1 in common. Put 1 parenthesis next to the greatest common factor that you just took out, and now use that as a multiplier to get back each of these terms. So -1 times x, -x. -1 times +3, -3. Now, look at this whole thing, but look at it as 2 terms. This is 1 term, this is 1 term. And one more time, take out your greatest common factor. What both of these have as a common factor is x plus 3. So still factoring the right side of this equation. And then what goes in the other parenthesis are these common factors that you took out during stage 1 and stage 2. Step 1 and step 2. So x squared minus 1. This can still be factored because this is difference of squares, and that can still be factored like this. You want to bring all of these down to first degree. You still have a second degree there, which means that you can continue factoring. Factoring is how you break down anything that's higher than first degree. You're breaking it all down to first degree by pulling the degrees apart by factoring. Okay, the way you factor difference of squares is x minus 1, x plus 1. You take the square root of that, put it there and there. You take the square root of the back number, put it there and there, and alternate the signs. Bring down that x plus 3. Once you have nothing but first degree factors, these are all first degree factors. You can make little baby equations, or you can just look at them and say, what would make this factor 0? An x value of -3. What would make this factor 0 if you put a 1 in there? So x equal to 1. These are what are called your zeros or your solutions. There are 3 words that mean the same thing. On a graph, they're called X intercepts. When you're looking for solutions for an equation, we call them zeros or just actually solutions. And the third one, you know that there are 3 solutions because this was a third degree function, third degree equation. So what would make this 0 is if you put a -1 right in there for x. So those are your zeros. Okay, find the y-intercept. Well, y-intercept, just like the last section, y-intercept in every section is when you allow x to be equal to 0. So in this particular function, we're going to let x be equal to 0 to find that y-intercept. So it's y, that's just another name for f of x. We're going to put 0 everywhere we see an x, so it's 0 cubed plus 3 times 0 squared minus 0 minus 3. And you can see that by plugging in x equal to 0 everywhere there was an x. This term goes away, this term goes away, this term goes away, leaving you with y equal to 3. So the graph has a y-intercept at when x is 0, y turns out to be -3, right at 0, -3. So that would be a point on the graph. Okay, turning points. Let's talk about the manner in which the graph turns at particular points. So if f of x is a polynomial function of degree n, let's just talk about the number of turning points. This is what we're talking about here. Then the graph has at most, let's say it's 4th degree, then the most number of turning points it can have is 1 less than that. So if you had a 5th degree function, the most turning points you can have is 4. It's always 1 less than whatever the degree is. Okay, what is the maximum number of turning points for this particular graph? Well, this graph is 3rd degree, the one that we've been working with throughout this entire page. Therefore, the number of turning points, the most times it's going to be able to turn is 2. That is, it can only have 1 less than that at the maximum. Not that it has to have exactly that many turning points, but that's the most number of times that it can turn. Okay, so let's go and take everything that we have discovered on this page and put it all together in the form of a graph. First, let's put the very first thing I think you should do is put the x-intercepts on the graph. Okay, so -1, 2, 3. This will be -3. Okay, and then another x-intercept was -1. And then another x-intercept was +1. Okay, next thing I want to talk to you about is, and you can go ahead and put the Y-intercept on there too. Y-intercept, so we'll do that next. One, two, three, there's your Y-intercept. I want to talk about what is going to happen at these X-intercepts because you have your ends. Let's review what our ends are doing. We decided that on the right side we're going to be going up and on the left side we're going to be going down. So why don't you get on the X-intercept that's all the way to the right, that end will be going up. Then there's the point all the way on the left. On the left side, we're going to be going down. So go down from that point. We need to know how to connect all of this stuff and what to do at each of these points. The Y-intercept, you're just going to be going through that point. But the X-intercept, you need to know, should I bounce off of the point or should I go through the point? And so we need to talk about multiplicity. So let's slide up here. Notice that where these X-intercepts came from, that each one of them came from a factor. This X-intercept came from this factor. And when it is of odd degree, that means you are going to go through the point. Whereas if any of these powers were even on these parentheses when we factored them, that would mean that you were going to bounce off the point. And we will get to those. But whenever the power on a factor that the X-intercept came from, when it is an odd number like this, it's a through point. Each one of these had a power of 1. Each one of them occurred one time. So we refer to these powers as the multiplicity. So each had a multiplicity of 1, which is an odd multiplicity. Therefore, they are all of these X-intercepts are through points. In other words, the graph is going to go right through rather than bounce off, rather than ricocheting right off of those points. And we can sometimes call those just touching points, where the graph just touches it and bounces off of it. Instead, we're going to go through them. So here I come from my left end. I'm going right through the -3, turning around so that I can hit the next intercept and also going through that. Continuing to move. Whoops, I'm not letting you see this. Okay, so I went from this end up to the very first X-intercept and I went right through it. And then I had to turn so that I could come right back down and go through the next point. And I still have to catch this Y-intercept as part of the graph. I must go through this point as well, which makes me turn around, go right through it, and then connect to the right end. And there's your graph. And you would get the same graph if you were to put it. Now, the calculator will give you exact height, and it'll give you an exact height on this. You don't have to do that when you're doing it by hand. I need to see that you understand multiplicity, how to get the X-intercepts, how to get the Y-intercepts, and that you understand end behavior. So this is what your graph looks like, all finished when you basically connect the dots using the mathematical theorems that we are going over in this section. Okay, next one. Okay, we're going to go through the same reasoning, put it all together in the form of a graph. So let's say that this is the function. What is the degree? This happens to be even degree. That means both of the ends are going to be moving in the same direction, either both up or both down. We look at this leading coefficient, and because the leading coefficient is negative, that means they're both going down. Okay, what is the degree? It's an even degree. What is the leading coefficient? -1. Anytime it's even degree, both ends move in the same direction. So what does the right side do? It goes down. What does the left side do? it goes down. I mean, if you want to put them both on the same line, this is the left side, this is the right side, we have to figure out how it twists and turns in between those two ends. So right side falls, and also the left side falls. Both sides go down. Okay, find the x-intercepts, also called the zeros, by allowing the y value to be equal to 0. So here I come up here, I'm going to let this y be 0, and I'm going to copy that right side of the function. Okay, so I can begin this factoring because I need to bring these all down to first degree factors so that I can find the x-intercepts all the way down to first degree. So first thing I noticed is that x squared can be factored out of all of these. If you want to get rid of the fact that there are negatives floating around in your leading coefficient, you can do that just to get this factor. You can go like this. You can divide both sides by -1. That'll get you 0 is equal to positive x to the 4th. Then this would be negative 4x cubed. And this would be positive 4x squared. So dividing by -1 just changes the sign, but you still have an equivalent function. We already know that both ends go down, so we did consider that leading negative to tell us what our end behavior does. So to get this factored, notice that every single one of these terms contains an x squared. And so I took out that x squared. So this is my common factor, and you're going to use this as a multiplier to get each one of these back again. So x squared times x squared is x to the 4th. X squared times negative 4x. Or let's see, no, x squared times negative 4x is going to be negative 4x cubed, and then x squared times positive 4 will get you that back again. Okay, let's come up here and continue factoring. You just copy it up here so I can continue working on it. Okay, so I pulled this out and I'm going to continue working on this trinomial. So breaking up that x squared into x times x, and then breaking up the constant into -2 and -2. Let's make sure this is what I started with right here. X times x, x squared. X times -2, -2x, and then -2 times x again, another -2x, giving me that -4x in the middle, and then -2 times -2 is positive 4. You can always just FOIL these out again, your factors, to make sure you factored it properly. So in the end, this is the factor I pulled out. It is of even degree, and then there was this matching factor which occurs twice, in other words, to a power of 2. It is important that you understand that these powers give us what's called the multiplicity. You cannot factor that any further. So now it's time to talk about what are the x-intercepts suggested by this factoring. So you look at this factor, which cannot be factored any further. And what would make this factor right here a 0 is if you plugged in x equal to 0. So this is one of the x-intercepts. Okay, this is an x-intercept. This x-intercept happens to be of multiplicity 2. In other words, the power on this factor is 2. Anytime your multiplicity is even like this, that means when it comes to placing this x-intercept on the graph, when you go to use it as a point for graphing, when the graph or the curve approaches this x-intercept, you are going to bounce, or in other words, you're going to bounce right off that point, or in other words, we could also call it that the graph or the curve touches the x-axis at that point and bounces right off of it. This always happens when your multiplicity is an even number. Okay, then there's what makes this factor 0, and that would be x equal to 2. If you were to plug a 2 in there, it would cause this factor to be 0. So this is another x-intercept, or what we call a 0. It also has a multiplicity of 2, and any multiplicity of 2 is even. Any kind of multiplicity that's an even number, you have another bounce point here, or another touching point. You can also call it a touching point. Okay, so we already know what the x-intercepts are, and we also know what we're going to do at those x-intercepts. When we do go to graph, we're going to bounce right off of them. And then we have this one. We're also going to bounce off of this one. Now let's answer those other questions to get a fuller idea of what the graph looks like. We need the y-intercept, and that comes from letting x be equal to 0, which is really easy to find. I mean, you can do it in your head. If you put a 0 in there and a 0 in there and a 0 in there, all of this would turn to 0. Okay, so you're putting 0 in everywhere you see an x. I don't know that I need to show this, but I will anyway, so people can follow it if they look at it later. This would be 0 plus 0 minus 0. So y is equal to 0. So when plugging in 0 for x, you get 0 for y. That's your y-intercept. Okay, so we did the y-intercept. We did our x-intercepts. We talked about what the ends are doing. And now let's talk about how many times we can expect this graph to turn. Okay, so this was 4th degree when we started. So the maximum number of turning points, 3. It's always 1 less than whatever the highest degree is. Okay, let's put all of this together on a graph. Okay, like I said, I suggested that you put the x-intercepts first, and there was only 2 x-intercepts, and those were 2, 0, and 2. Okay, they were 0 and 2. You are going to bounce off of this one, bounce off of this one. So I'm going to put that there. I'm not going to bounce off of them yet. 1, 2. This will be 2. I'm going to put my ends in place. With my ends, we determined that we were going to go down on the right, underneath the rightmost point, and we're going to go down on the leftmost side. And these are the points that are furthest to the right and furthest to the left. So you're going to always line up your ends with the rightmost point and the leftmost point. Okay, so as I actually go from these ends and I approach these points, don't forget to also put the y-intercept, but you can see from our work that the y-intercept was just 0. So by us putting this x-intercept, it really served as the y-intercept also. So now as we approach, we are not going to go right through it. We're going to bounce off of it, turn, come back up to hit this point, and right back down again. And you can put any of these graphs in your calculator. You just can't know how to only do them by calculator when it comes to the test. You have to show that you can answer any of the questions that I have asked above and then put all that information together in a graph. So if you put this in your calculator, this is what it would look like. It would come up to the x-intercept 0, bounce off it, ricochet right off of there and start coming down, but then have to quickly go right back up to hit the other point, but then have to come straight back down again to connect with the end on the right-hand side, and you would end up with a graph like that. Okay, moving to this next example. The next example, Thank goodness is already factored, so we can, answer the questions much more easily, but you do have to think about what is the degree of the polynomial. This portion right here would give you x to the second degree. If you were to FOIL it out, the highest term, the term with the highest degree from just that portion would be x to the second degree, whereas this has just an x to the first degree. Well, when you're trying to determine what the degree is, you need to add up these degrees. So the highest degree term would be x to the third degree. We saw this in another example that I already went over. And then the leading coefficient would just be this number times 1 right there times 1 right here. So -2 times 1 times 1 would be the coefficient for here. So this is what we are going to use to apply the leading coefficient theorem. Okay, this is odd degree. That means that the ends are going to go in opposite directions, and the leading coefficient is this -2 right here, which happens to be a negative number. So whenever we have an odd power, the ends move in opposing directions. Not in the same direction like when it's an even degree, but in opposing directions. So that can mean two things. It can mean the right side goes up and the left goes down, or it can mean the left side goes up and the right side goes down. When this is a positive number, right goes up, left goes down, but it's the reverse of that when the leading coefficient is negative on an odd degree. So this time the left is going to go up and the right is going to go down. And then we're going to figure out what's happening in the middle. Okay, that's the question to be solved through all of these answers right here. So is the degree of the polynomial odd or even? It is odd. It's third degree, as I discussed up above. What is the leading coefficient? -2. Determine the end behavior. Does the right side of the graph rise or fall? This is the right side right here. It falls. It goes down. Does the left side of the graph rise or fall? So this time we're talking about the left side. This is the left side, and it goes up. So it rises. Something goes down, it's falling, and something goes up, and then goes up, it's rising. What are the x-intercepts? We've been practicing that in every problem. So we said that we do that by allowing the y to be 0. So here's your y up here. That is 0, and we're getting a lot of practice at factoring and figuring out how to solve these equations for x. Now this already is factored, so that's a good thing. Sometimes it makes it harder to tell what the overall degree is. We had to, know that, hey, you would get a second degree term out of this multiplied by the highest degree here as first degree for a total of third degree. So you have to be able to think of that, but it's good for this part of the problem where you would need to factor anyway. So this is as factored as it can get. So you want to figure out what are the x-intercepts. They are just the numbers that would make each of these factors 0. So the x-intercepts are what would make this factor 0 if I plugged in x equal to 1. It would be 1 minus 1, 0. And even if you're squaring it and multiplying by -2, it would still be a 0 here. What would make, and the multiplicity, let's keep an eye on this. This 0 came from this factor. This factor had an even multiplicity. The power on the factor is the multiplicity. So because it had an even multiplicity, we are going to bounce off that point. Or in other words, we're just going to, the graph or the curve is just going to touch that x-intercept and bounce right off of it. This, on the other hand, the other x-intercept, in other words, what would make this 0? -2. That has a power of 1. 1 is an odd number. So therefore, this 0 had an odd multiplicity because this came from this, the power was 1. So this had an odd multiplicity, and therefore this is going to be a through point. You're going to go right through that x-intercept. This one we're not going to go right through, we're going to bounce off of it. Finally, the y-intercept, that comes from letting x equal, allowing x to be 0. So in the function, everywhere I see an x, I'm going to put a 0. So 0 minus 1 squared, and then 0 plus 2. There's my zeros all plugged in for the x's. So this would be negative 2, 0 take away 1, negative 1. There's a square on it, and there's a 2 right here. So this would be negative 2, and you can put in your calculator if you want to. Negative 2 times 1, because negative 1 squared is 1. And times negative 2 would be negative 2 times 2, negative 4. Okay, so the y-intercept is when you use an x value of 0, you get a y partner of negative 4, and that is your y-intercept. Let's put all these things together to create the graph. Okay, your x-intercepts, and you can just be looking at what you did above. You don't have to keep writing it. The x-intercepts, one more time, are x equal to 1. And we are going to bounce off that point, or just graze the x-intercept and bounce right off of it. The other x-intercept was x equal to negative 2, and that one we're going to go through. You may want to make these little notes when you go to create your graphs by yourself. And then the y-intercept, you can see right there is 0, negative 4, 1, 2, 3, 4. That's 0, negative 4. My x-intercepts are 1 and negative 2. Okay, place those ends where they belong. Remember, we're going down on the right, down underneath the leftmost point, and upward above on the right. This for the right end, we're going to go down, and on the leftmost point, we're going to be going up. Okay. Here is your point that is furthest to the right. You're going down on that end. Okay, so just paste the end right there, and we're going to come up to this point and do whatever we're going to do there. And then on this end, your leftmost end, you're going to be rising. So put the end above it so that you can rise. Now, from these ends that I've pasted in place, travel to the x-intercepts. Let me just put this one a little bit lower so you can see me moving towards the points. Okay, so at the 1, I'm supposed to bounce right off of it, not go through it. Don't go through the x-axis. So bounce off of it, turn and come down, catch that y-intercept, turn again, travel to the negative 2, check what you're supposed to do there. You're supposed to go right through it and up through that end. All these things have to be connected, and then you can trace over it and refine it, and that is what your graph looks like. Most number of turning points it has was it turned here and it turned there, so 2 at most. We've respected these x-intercepts, bouncing off this one but going through this one, and we have the proper end behavior. Okay, last problem. In this one, we see one more example. This time it is not factored. So I'm kind of trying to take you back and forth between ones where you're going to have to practice your factoring skills and others where it's already factored. You're going to have a combination of different types of problems. Okay, so let's see. What can we do? Okay, for the given function, create a graph by hand. Discuss the end behavior of the graph and show all algebraic calculations for the x-intercepts. Do the y-intercepts of the graph. Is the degree of the polynomial odd or even? Okay, it's even. You look at the highest degree. It is even because the highest degree is 4th degree. You're only looking at the term with the highest degree to determine the degree. What is the leading coefficient? number in front of it, 1. Okay, this is your leading coefficient, and whenever your leading coefficient is positive, combined with an even degree, that means both ends move in the same direction. And specifically, because that leading coefficient is positive, both ends are going to be going like this. Okay, right end goes up, left end goes up. Does the right side of the graph rise or fall? Well, right side goes up, that's considered rising. Does the left side of the graph rise or fall? Well, the left side goes up also, that's considered rising. Find the x-intercepts by letting y be equal to 0. So, if we're going to let y be equal to 0, this is the y. That's where your 0 goes. And then you're going to have x to the 4th minus 2x squared plus 1. So we have to work at factoring this ourselves because it's not factored. So let's see, if this is 4th degree, it's a 4th degree trinomial. We're going to break up this front term, asking ourselves what times what would be 4th degree, and that would be x squared and x squared. And then what times what would be 1, but yet giving us a -2 as the middle term. We can make this -1 and -1. Let's check it to make sure that we're getting the same polynomial that we started with, x to the 4th minus 2x squared plus 1. So if I considered foiling this back out to check my factoring work, it would be x squared times x squared, x to the 4th, good. X squared times -1, negative x squared. Here's another negative x squared for a combination of -2x squared on that middle term. And then -1 times -1 is +1. So I did factor it properly. But then let's consider the fact that it is the same expression both here and here. And you can still factor further. This is the difference of squares. You can take a square root of this and you can take a square root of that. That means that those can be factored further. So let's factor this further as the difference of squares. Take the square root of that, which is x, goes there and there. And then take the square root of the 1, goes there and there, and alternate the signs. Likewise, this can be factored in the same manner because it's the same expression. X plus 1, x minus 1. When you rewrite this so that you're showing yourself the multiplicity, because the power on the factors determines whether you're going to bounce or go through the x-intercept. So let's rewrite this in a way that's going to reveal that. As far as x plus 1, that occurs twice, so to the 2nd power. And x minus 1 also occurs to the 2nd power. Okay, so what are the x-intercepts? Well, here's one x-intercept. It is the value that makes this factor 0, -1. The multiplicity that belongs to the factor, that gave me this x-intercept. That multiplicity is even. It's a 2. And therefore, you are going to bounce right off of that point. At x equal to -1, you're going to bounce off the point. What makes this factor 0 is x equal to +1. It also has a multiplicity that's even. And therefore, multiplicity is just these powers right here. Therefore, you're going to bounce off that point as well. Okay. All right, so we made some little notes. Y-intercept, just let the x be equal to 0. So, again, in this function right here, it's y is equal to, I'm going to put a 0 there, and be left with the 1. Y is equal to 0 to the 4, so that term's going to be gone. -2 times x squared, I'm putting a 0 in there, and then plus 1. So this would be 0, this would be 0, leaving you with just the 1. So your y-intercept is when letting x be 0, you end up with 1 as a y partner. So this is my y-intercept, and I'm going to put all of this on the graph. Okay, so I have an x-intercept of -1, an x-intercept of +1. I'm going to bounce off this point, bounce off this point. I also have a y-intercept of, let me move my little notes down here. And you can just try to memorize what you're doing. Just kind of hold it all in your head. And then at 0, 1, there's my y-intercept. Now let's try and put the ends in place. The ends are lined up with the leftmost point and the rightmost point. We are going, let's review what we're doing on our ends. Both ends are going up. So this end is going to go up, and this end is going to go up. That's how we're going to finish those graphs. Now, we travel from those ends to our x-intercepts and do whatever we're supposed to do. We're supposed to be bouncing off these points, not going clear through the x-axis. So we're going to go like this. Bounce, in other words, ricochet right off that point and turn to go and catch that y-intercept. Turn to go and catch the other x-intercept and back up to catch that left end. And that's what that graph looks like there. Okay, I went from this end down to the x-intercept, but bounced off it, which means I have to turn right away as soon as I hit it. Back up to catch the y-intercept, turning again. Bouncing means turn as soon as you touch it and go in the opposite direction. It was coming down, I hit it, and then I went right back up to connect to that left end. And that's the final graph there as we put all the information that we gathered on this page together in the form of a graph. And I believe that is the last question. Okay, that completes section 4.2.